Let's be honest, large language models, or LLMs, can feel like pure magic. I mean, they write emails, they can code entire applications, they can even compose music. But here's the thing, it's not magic, it's math. And over the next few minutes, we're going to pull back the curtain and show you exactly how it all works.
Let's start with something you probably use dozens of times a day without even thinking about it. You're typing a text message, and your phone just knows the next word you want to type. It's almost creepy, right? Like it's reading your mind. Well, that tiny little feature is actually a perfect window into how even the most powerful AIs on the planet operate. It's all about one simple idea: prediction. Okay, so at its absolute core, a large language model is just a very, very fancy prediction engine. Its only real job is to look at a bunch of words and then calculate, with mind-boggling precision, the probability of what word should come next. So if you give it the sun sets in it's going to say west. Not because it knows anything about astronomy, but because it has scanned billions upon billions of sentences where west was the most statistically likely word to follow. That's the big secret.
Now, this idea of treating language like a math problem, it's not new. This has been building for decades. You can go all the way back to Claude Shannon in the 40s, then you get these early chatbots in the 60s, and statistical models in the 80s. But the whole game changed in 2017 with a new architecture that could finally understand deep context. It's called the transformer.
But wait, before a model can predict anything, it has to solve this gigantic problem. Computers don't get words. They don't understand happy or sad. They only understand numbers. So the very first step in this whole process is translating our messy, beautiful, complicated language into a mathematical format that a machine can actually work with. That translation process starts with something called tokenization. So instead of seeing a big word like unbelievable as just one thing, the model is smart enough to break it into its meaningful parts: un, believe, and able. This is incredibly efficient, because now the model understands the concept of what un means at the beginning of a word, or what able means at the end, and it can apply that knowledge to thousands of other words it sees.
Okay, so once we have these little tokens, they get their meaning through something called embeddings. Now just think of this as a gigantic, multi-dimensional map. Every single token is a dot on this map, and words with similar meanings, like puppy and kitten, get placed really close together. This map is so precise, you can literally do math with words. You probably heard of this one. If you take the location for king, subtract the location for man, and add the location for woman, you land right next to the dot for queen. It's an algebra of meaning. It's just wild. So, we've turned words into numbers that have relationships and meaning. That's a huge step. But language isn't just a jumble of words. The order and the context are everything. This is where the next massive leap forward happened. We moved away from simple word chains to a model that could see the entire picture all at once. The older models, which were called n-grams, had a really short memory, like ridiculously short. They would predict the next word based on only the 2 or 3 words that came right before it. So, yeah, they might know that the word river is often followed by bank, but their memory is so limited they'd have no idea if you were talking about fishing or finance. They were totally missing the big picture. Just look at the difference here. It's night and day. N-gram models, they had this tiny little window of context. Transformers, on the other hand, can see the entire sentence, or even the entire book, all at once. They use this incredible mechanism, called attention, to constantly figure out which words are most important to which other words, no matter how far apart they are in the text. This is the jump from just stringing words together to actually understanding deep semantic relationships. And this whole revolution, it was kicked off by a single research paper with this incredibly bold, almost arrogant title: Attention is All You Need. It's the paper that introduced the transformer and its secret weapon, self-attention. For the very first time, a model could look at a pronoun like it and scan the whole text to figure out exactly what it was referring to. Context was no longer a problem. So we have this incredibly powerful architecture, the transformer. But how does it learn to make good predictions in the first place? Well, the answer is a process that's actually inspired by one of the most basic principles of learning: trial and error. This is my absolute favorite way to think about how a model learns. So imagine you're standing on a huge mountain, but it's completely covered in fog. Your goal is to get to the lowest point, the valley. You can't see anything, but you can feel the slope of the ground right under your feet. So what do? You take one step in whatever direction is most steeply downhill, and then you do it again and again. In the world of AI, that slope you're feeling is the model's error rate. Every little step it takes is a tiny adjustment to its internal settings, always trying to reduce that error. This whole process is called gradient descent, and it's how the model slowly but surely walks its way towards the best possible answers. But just being statistically correct isn't enough, right? We need these models to be helpful, and maybe more importantly, safe. And that's where this really clever process called reinforcement learning from human feedback, or RLHF, comes in. First, the AI generates a few different answers to a question. Then, actual humans come in and rank those answers from best to worst. All that ranking data is used to train a separate reward model whose only job is to get good at predicting what humans will like. And finally, that reward model is used to fine-tune the main LLM, basically guiding it to give answers that are not just right, but also aligned with what we actually want. So what puts the large in large language models? Well, it turns out that when it comes to these things, scale isn't just important, it's everything. Just by increasing the amount of data, the number of internal parameters in the model, and the sheer amount of computing power, researchers unlocked abilities that honestly seemed like science fiction just a few years ago. I mean, just to put this into perspective, it's estimated that GPT-4 has over 1 trillion parameters. Think of each one of those parameters as a tiny little knob that the model can tune and adjust as it learns. With over 1 trillion of these knobs, the model can map out the patterns and nuances of human language in absolutely unbelievable detail. This is what lets it go from just predicting the next word to generating totally new and coherent ideas. But having that immense scale comes with a huge risk. It's called overfitting. Imagine a student who, instead of learning algebra, just memorizes the answers to the practice test. They'll get 100% on that test for sure, but then they'll completely fail the final exam because they never actually learned the underlying concepts. An overfit model is exactly the same. It gets so good at its training data that it can't handle anything new because it memorized facts instead of learning the rules. So how do you stop your genius model from just memorizing everything? Well, researchers use a bunch of tricks called regularization. One of the cleverest is something called dropout. While the model is training, it's forced to randomly just turn off some of its own internal connections. It's like forcing it to solve a problem with one hand tied behind its back. This prevents any one part of the model from becoming too powerful and forces it to find multiple different ways to get to the right answer. It makes it way more flexible and a lot less likely to just memorize. You know, when you put all these pieces together, the data, the algorithms, the incredible hardware, the human feedback, what you end up with is so much more than just a piece of software. What you're looking at is a true marvel of modern engineering. And that is not an exaggeration. When you think about the trillions of data points scraped from the internet, the global collaboration of researchers, and these massive supercomputers that have to run for weeks or months on end, building a state-of-the-art LLM is an engineering feat on the same level as the Hoover Dam or the Apollo missions. It's a monument, but it's built not out of concrete and steel, but out of computation and data. And this story is nowhere near finished. The next frontier is already taking shape as we speak. We're looking at things like sparse models that are way more efficient, something called federated learning that can train AI without ever seeing your private data, and of course, true multimodality, models that won't just understand text, but images, audio, and video all at the same time. The revolution is really just getting started. So, we'll leave you with this question to think about. We have built an engine for understanding and creation unlike anything in human history. The technical challenge was enormous, for sure, but the real challenge is just beginning. It's not so much about how these machines work anymore, but about how we, all of us, choose to live and work alongside them. Thanks for watching.